So in this lecture, we're going to look at two number theory theorems and see how we prove them. Okay, and this first one here is going to follow a very similar pattern to what we've seen before. We really are going to take this straight from our definition of divisibility, right? And what this is saying, you remember we have a property in algebra that says if A equals B and B equals C, then A equals C. In other words, if you have this bridge here in the middle, we can kind of skip it and just say the endpoints are equal to each other. And that's called the transitive property. And this is what this is saying here, right? It's kind of a transitive property for divisibility. All right, so I want to start this off. We've kind of done this before. I want to start this off by focusing on where we want to end. What I want to show is that A divides C. And think about what our definition says, right? What does it mean for A to divide C? Well, this is going to be our goal. Show that there exists, let's use Q. There exists an integer Q such that C is equal to Q times A. I want to block this off. Now that's not actually part of our proof, right? I just want to have it clear in everybody's minds. That's where we need to end up. Okay, so how can we do that? Well, let's start with our definition again, right? If A divides B, then there exists an integer M such that B equals A times M. Right, and similarly, if B divides C, then there exists, and we've got to use another variable here now, right? There exists an N, an element of Z, an integer N, such that C is equal to B times N. Okay, good. So where am I going to go next? So I'm thinking about where I want to end up. In the end, I need to have a statement about C, right? So I'm thinking I'm going to kind of focus on this part here, right? If C is equal to B times N, all right, well, what else? Well, remember up here, B is equal to A times M. Okay, good. So let's substitute. This is equal to A M N, and M and N, if I group these here, M is an integer, N is an integer, so their product is an integer. So I'm going to say let Q equal M times N, and that is an integer. So C is equal to Q times A. Well, not just for some integer Q, I actually know the integer Q, right? For Q is equal to M times N, and that's what I needed to show, right? That's what I needed to show. Therefore, we can conclude that A divides C, which is what we wanted to show. Okay, this one is a little bigger, right? It's going to require a little more work here. I want you to take a minute, read it through, right, and then we'll start by looking at an example. All right, so what this is saying is if I have two integers, B and C, and they have a common divisor, not necessarily the greatest common divisor. This is true of any divisor, right? So if A divides both of those numbers, then A also divides any what's called a linear combination of those numbers. Right, so I can take those two numbers, multiply them by any other integers, add them together. A is still a divisor. Really? Okay. Well, let's take a look. Right? Let's take a look. Think about a specific example first. Right? So let's say I say let A equal 2, and then I need two numbers B and C that A divides. So I'm going to say let B equal, I'm going to pick kind of off the wall numbers, right? Because I don't want to be predictable about this. So let's let B equal 10 and C equal 82. Right, just kind of picking stuff off the top of my head. All right, then what the theorem is saying is that I can pick any two integers, u and v, right? Any two integers. If I multiply b and c in respectively by those numbers, add them together, a has to go into that sum. Okay, so let's pick u and v. Again, I'm just kind of picking at random here. Let's let u equals, how about u equals -6, right? They're negative integers, right? So let's pick -6. Then for v, I'm going to set let v equal, and I want to be careful here, right? Because we're trying to be generic as possible. I'm going to say let v equal 3. I specifically avoided picking an even number, right? Because I already know that the sum of two even numbers is even, so I don't want to accidentally come up with a special case, right? So I'm kind of trying to pick these to be as different as I can make them. All right. Now, what is BU plus CV? Right, that's 10 times -6 plus 82 times 3. And my big question here, remember, this is my A is 2. My big question here is, does 2 go into this evenly? Right, well, let's see what we get here, right? This is -60 plus 8 times 3 is 24, 246, which is, I believe, 186. Yeah, 186 is 2 times 93. So yeah, 2 does divide BU plus CV, right? Now, why? Let's see if we can narrow this down a little bit, okay? And in a way that's going to help point us towards what we're going to do in the proof, right? So I actually want to cycle back around here, jump back up here to this original row, right? I can pull a 2 out of this. Remember, I'm trying to show that it's divisible by 2. If I take a 2 out, this becomes 2 times 5 times -6 plus 41 times 3. This is an integer, right? That's an integer, and that's what I needed to show, that this sum is equal to 2 times some integer, right? And that is how my proof of this is going to kind of progress, right? So let's see. I'm going to go back. See, I think I can fit this in down here. So that was just my example, right? Kind of getting a feel for what this is saying. Now let's see if we can actually prove this. Okay. A divides B, therefore there exists an integer m such that B equals m times A. It's just a definition. Now I'm going to do the same thing with A and C. A divides C implies there exists an integer n such that C is equal to n times A. All right, well now let's look at this BU plus CV. All right, I'm going to do something very similar to what I did in the last proof. I'm going to do a little substituting. B is m times A, so this is MAU plus CV. That's NAV. All right, but now this is why I wanted to backtrack and look at this, where I pulled out that common 2. Notice that there's a common A here. Okay, awesome. Pull out that A. This is A times MU plus, make sure I don't mix my variables up here, MU plus NV. Well, mu plus nv is the product and sum of integers, so that is also an integer. So let's do what we did before, really kind of be formal about this. Let q equal mu plus nv, that is an integer. So bu plus cv equals a times some integer, right? That's what I needed to show. Therefore, b divides bu plus cv, right? And that's a period, right? Get punctuation in there, and that's what I wanted to show, right? That was the result I needed. Okay, so two little theorems, right? I really want you to hold on to that second one, right? In the next lecture, we're going to take a look at the process for finding the greatest common divisor of two numbers. And then you probably learned, you may have forgotten it, but you learned how to do this back probably in, I don't know, 5th grade or something like that. It's the one where you write out the prime factorization of both numbers, and you take the things they have in common and then do some stuff with the exponents, and out comes the greatest divisor. I was going to say that's great, but not really. It works well enough for small numbers, not so much for large ones. All right, so what we're going to do in the next lecture is we're going to take theorem 3.2 there, and we're gonna use that to come up with a method for finding the greatest common divisor that is significantly more effective than the method you learned back in the 5th grade.